Hello everyone, we're going to be doing some math today. Today I'm going to be talking about the computational complexity of English, and if you don't know what any of those words mean, I hope you know what English means. But if you don't know what computational complexity means, don't worry about it. You shouldn't need that much math background to understand this talk. I'll be explaining everything as I go. Basically, we're going to be talking about how computers can understand English. And anytime we talk about this sort of subject, we call it natural language processing. Natural language basically means any language that humans speak. Say like English, French, German, Chinese, all of these languages are natural languages. And you can contrast that with computer languages like Java and JavaScript and that sort of thing. So, first thing, why care? And the reason is because this is so relevant to everything you do nowadays. Everything we do is connected in some way to technology. And so I just pulled up a simple example. I typed in "why is the" in Akoja, and it gave out a bunch of suggestions for what I could search. How does it know what I'm going to type next? This is one example of a question that we could address using natural language processing. How does the computer understand English enough in order to suggest to me things that it thinks that I want to know about? Okay, so you might say, well, this is just a simple statistical analysis. You don't really have to understand English to answer this question. You just need to know what most people put into the search engine, and they have a lot of data, and they can just simply sort out which is the most common request, and then give you that on the search engine. But here's another example. This is in Gmail. If you type something like this, you can write "Dear Dr. Example, I hope you are doing," and then it automatically knows what you're going to type next, "doing well." When this first came out, I was a little bit creeped out about it, but now it's just a thing that it's present in our lives, I guess. Alright, but for this example, the computer really has to understand what the question is in order to answer it. So how long can a lobster survive out of water? And you can see that in this case, WolframAlpha has misunderstood the question, is given some sort of nonsense answer, and the weird thing here is that it understands all of the individual words. So it understands lobster, it understands how long, it understands survive. You can see it knows that the question is something about the lobster's maximum recorded lifespan, and but the curious thing is that it's interpreted out of as division, instead of being physically outside of the water, and so it's giving you this nonsense garbage answer. And so the question is, how can we program a computer to understand how to put together all of these words, even if it understands what all of these words mean? And how can we, program a computer to understand what a sentence means? Because anytime you have, say, like Siri, Alexa, Google Home, WolframAlpha, you input your input as text, and it spits you out an answer. How does it understand what your input is? Alright, so as I said, today we're going to be talking about natural language processing, and the basic definition is processing English through machines. And obviously it doesn't have to be English, it can be any natural language like French, Spanish, etc. And it is an extremely broad field. It involves many, many, many different fields. So knowledge from all different places comes into play here. You can think about psychology, you can think about computer science, mathematics, statistics, linguistics. All of these fields are somewhere present under the large umbrella of natural language processing. Alright, so let's sort of narrow down where we want to talk about for today. So natural language processing is an incredibly broad topic. We want specifically to understand what it takes to build an algorithm that will tell whether a sentence is grammatical or ungrammatical. So maybe once we find an algorithm that can figure out if a sentence is grammatical or ungrammatical, we've come one more step to understanding how a sentence works and how a machine can understand a sentence. So even more specifically, we want to identify how complex an algorithm we need to model English grammar. And of course, we'll define in more rigorous terms what all of these words mean later, so complex, algorithm, things like that. But really, we just want to figure out how we can model English sentences in a way inside a machine that is helpful for understanding what an English sentence means. Okay, so where do we start? We're going to use tools from a field of math, or you could say computer science, called automata theory. And all of these ideas were developed say in the beginning of the 20th century, so long before modern computers even existed, people were thinking about these ways and how do we understand computations, how do we understand machines and how machines think. So don't worry, we'll go over lots of examples. You don't need any background knowledge on what automata theory is or anything like that. We'll explain everything along the way. Alright, so the first thing we need to do is establish some definitions. Alright, so what's the first thing you learn when you learn English? You learn the English alphabet. And we're going to start with the same thing here. So we're going to define an alphabet as any non-empty finite set. So let's just parse for a second what that definition means. So finite, because we can't have an infinite number of things in our alphabet. That doesn't make any sense. And non-empty, because we can't have an empty alphabet. We need at least one thing in our alphabet. So let's just go over some examples right now. So I'll just write here alphabets. I originally gave this talk as a Blackboard talk, so it's a little bit awkward on computer, but it's okay, we'll charge through it. So, what we usually use to denote alphabets is this little capital letter sigma thing, and one example of alphabet we could have is just A, B, C, D, dot 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 all the way up to Z. So that's the usual English alphabet. But this definition is pretty flexible, so we can really, put anything inside the set that we want. So for example, we could have the, alphabet, you could say, of digits. So we could have the alphabet 0, 1, 2, 3, dot dot dot, all the way up to 9. And you might say, well, this is a little bit odd, why would we allow this to be an alphabet? But you'll see that it actually makes things useful later on. So another simple alphabet we could consider, and this is an example I'll sort of be using throughout the talk, is we could have the alphabet of American currency. So American coins, there's the penny, there's the nickel, there's the dime, there's the quarter, and there's other coins, but I'll leave them out for now. And so this is one example of an alphabet you consider. That's a little bit more abstract, but that's useful for playing around with examples. So the next thing you learn in English is how to put together letters from the alphabet into words. And we're going to be using sort of the same thing here, except instead of words, we're calling them strings. So a string is just some sequence of elements from the alphabet. So let's give you some examples. I'll write strings here. So with the first alphabet, what are some examples of strings we could have? So we could have, A, B, C. That's one example of a string we could have. You could have, G, E, T. That's another example of a string we could have. You could have D, O, G. And of course we can have like any length of string we want as long as it's finite. So we could have, a string of 6 characters. So D, O, G, G, E, D. And we can even have a string of no characters. It turns out that's a little bit useful to consider too. And the way we write the string of no characters is with this weird looking epsilon symbol. So that just means the string with 0 characters inside of it. Okay, and we can do sort of the same thing with the other alphabets. So we can consider, strings from the alphabet of, digits, maybe like 0, 1, 2, or just 5, or we could have like 3, 3, 3, 3, or we can also have the empty string again, right? So these are all examples of strings using the second alphabet, so the alphabet of digits. And just to complete off the example, we could have the strings of American coins. So we could have penny, penny, we could have penny, 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 we could have nickel, quarter, we could just have a single dime, or we could have no coins, right? That's another option. Okay, so these are all valid options. And so what we're really interested in is a language. So we're going to consider a language as just a set of strings. So that's going to make a little more sense as we go through some examples. So, let me just give a little bit more space here. Boop. Boop. Okay. So one example of an alphabet we could have, a language we could have, is the language of all valid English words. Okay. So let's look at the strings we figured out in the previous example. So we have ABC, get, dogged, and the empty string. Some of these words are valid words, and some of them are not. So we're going to consider the language of all valid words. So usually we denote language with an L for language. And it's going to equal the set of all the possible English words we could have. So this would be like the, and cake. My handwriting of this touchpad is awful. But this would be like the language of all possible valid English words. And similarly with the second alphabet we considered, we could have the language of all prime numbers. So that would be like 2, 3, 5, 7, 11, etc. So that's another possible language you can consider. And remember, a language is just a set of strings. So it's just a set of these things over here. And for the third one, we can consider maybe the language of all coins that add up to 25 cents. So 25 cents could be a quarter, it could be 2 dimes and a nickel, it could be a dime and 3 nickels. All of these things would be valid strings in our language. Alright? And so the central problem we're going to be considering is something called the decision problem. So if we're given a string, how do we tell whether it's in the language? So let's reword what the decision problem is for all three of the languages we're considering. So I'll just write that big here because it's important. Decision problem. Decision problem. Alright, so for the first example, if we're given a list of letters, how do we tell if it makes up a valid English word? So how do we know that ABC is not a word, but get is a word, and dogged is a word, but the empty string is not a word? Well, one algorithm for doing this is simply get out your favorite dictionary, Merriam-Webster or something else, and just flip through it and check if the list of letters that you've been given is in the dictionary. If it is in the dictionary, then it is in the language, and if it's not in the dictionary, it's not in the language. So that's one possible decision procedure for solving this type of decision problem, right? So for the second example, it would be given some list of digits, so some sort of number. How would you tell if that number is a prime number? One really simple way to do it is check every number that's less than that number and check whether it's divisible by that number. So if you think about 5. Well, 5 divided by 2, that doesn't work. 5 divided by 3, that doesn't work. 5 divided by 4, that doesn't work. And so we know that 5 is prime. Now, there are much more efficient ways to do it, but that's one example of a way we could solve this decision problem. And then for the third example, how do we tell if you're given like a bunch of coins, how do they tell if you add them up, if they add up to 25 cents? So one simple way is just, to count them up, and then if it's over 25 or if it's under 25, then it's not in the language. But if it's exactly equal to 25, then it is in the language. So, for example, NQ, N is 5, and Q is 25. And if you add those together, you get 30 cents. That's not 25 cents, so it's not in our language. But if you consider a string here, like DDN, 10 plus 10 plus 5 is 25. And so we know that DDN is in our language. So that's one way to solve the decision problem. Now there are a whole sort of decision problems. Some of them are very complicated, some of them are very easy to solve. And the relevant decision problem that we're going to think about is like this. So this is basically the problem that we'll be answering for the rest of the talk. And we're going to do something a little bit strange, but it'll make a little bit more sense as we go on. We're going to consider the alphabet of all English words. So that'll be like the, and, a, cake, etc. It's going to be a very big alphabet. We're going to assume there's a finite number of words. And the strings in our language is just going to be all ways of putting these words together. So we could have maybe like the, and, cake, that would be one string. We could have maybe cake, he hit. And then another valid string would be, their bat. Just any sequence of English words is a valid string under this framework. And you could have also, of course, the empty string. That's always another possibility. And the language we're going to consider is the language of all grammatically correct English sentences. So one example of something in this language would be, he ate a cake. That is a grammatically correct English sentence. So that would be in our language. He ate a cake. Another example would be, she saw a bat. These are all examples of possible things that we could have in our language. And it's going to be an infinite number of possible strings we could have. And so this is a decision problem we're going to solve. So now you can see that we've reframed our question. So we have a set of all the possible grammatically correct English sentences, and we want to figure out, if we're given a string of words, how do we figure out if that string of words is in our set or not? So in other words, if we're given like a string of words like cake, he hit, there, how do we tell if it forms a grammatically correct English sentence or not? So this is the question we want to answer, and this is called the decision problem. And this is the question that we want to take the rest of the talk to understand. Okay. So in other words, is a given string grammatical in our language? That's the decision problem. That's the most fundamental question. So, if you don't remember anything from this talk, except for the decision problem, you've come away with the most important thing. So let's see. One way to solve the decision problem is something called a finite state automaton, and that sounds really scary, but it's really just a really big word for flowchart. So we're considering a flowchart. So let's think about how this looks like. We're going to solve the decision problem for the language, a sequence of coins that add up to 15 cents, and the language we're considering the alphabet we're considering is nickels and dimes. So given a string of nickels and dimes, we want to figure out if it adds up to 15 cents. So one way to do this is a simple flowchart model. So let's say we start at 15 and we count down to 0, right? So we're going to start at 15. And to indicate that we start there, I'm just going to put this arrow towards it. And then, maybe every time we see a nickel, we count down by 5. So if we see a nickel, then we count down by 5, we get 10. If we see another nickel, we count down by 5 again. We get 5. And then if we see another nickel, we count down by 5 again, we get 0. And that's our goal, so I'm going to put another circle around it. It'll be 2 circles. And we can do a similar thing for dimes, right? If we're at 15 and we see a dime, we're going to count down by 10. So that lands us at 5. And then if we are at 10 and we see a dime, we're going to count all the way down to 0. And that's going to be a dime. So there are a couple different parts to this. So there's something called the start state. So right here, we're going to call the start state. And then we have a final state. And we could have multiple final states if we wanted, but in this example we just have one. So we're going to call that the final state. And then we have a bunch of transitions in between them. So all of these arrows are transitions. Okay, so how do we use this? Let's do one example. So let's say we have a nickel and a dime, and I want to figure out if it adds to 15 cents. Well, I start right here, and then the first coin I have is a nickel, so I follow this arrow here, and I'm here, and then the second coin is a dime, so I follow this arrow here, and I land in the final state, and that means the nickel and the dime do add up to 15 cents. So anytime I land up in the final state, that means this given string is grammatical in our language. So in other words, the nickel and the dime add up to 15 cents. But we can consider another string of coins. So let's say we had 2 nickels. Well, if we start here and we follow the nickel path, we get to 10, and if we follow the nickel path again, we get to 5. And now you see we landed in a state other than our final state, and that means our given string is not grammatical in the language. So in other words, if you have a nickel and a nickel, they do not add up to 15 cents. And that may seem a little bit obvious, but it's just a little toy example before we consider more complicated examples. Okay. So over here I have like a sort of a formal definition as to what a finite state automaton is. And again, you can think of the finite state automaton as a flowchart basically. And I just include this for completeness really. It's not really important to understand what's going on here. All that matters is that you can sort of mathematically formalize this concept. So what really matters is that we can mathematically formalize it. So in other words, mathematically we have a set of states. So we have an alphabet, nickels and dimes, and then we have some sort of function that tells us how to go between them. So that's represented by these arrows. So let's write arrows. We have a starting state, which is 15, and so on. So we can represent this flowchart completely mathematically instead of inside. So the picture is easier for us to see, but really it's some sort of mathematical object that we're dealing with. Okay, so anytime we can make one of these flowcharts, so one of these finite state automaton for a language, we're going to call that language a regular language. And why do we care about regular languages? The reason is they have nice computational properties, so they're really easy to work with. Anytime that you have a regular language, it's really easy to figure out if something is inside that language, because you just follow the flowchart, and then when you get to the end of the flowchart, then you know if it's in your language or if it's not in your language. And we just did an example of that. So if you're familiar with big O notation, which some of you might be, we can say that this runs in O of n time, where n is just the length of our string. So the point is that if we have a regular language, if we have this finite state automaton, then it's really easy for a computer to do. So if English were a regular language, it would be really easy for a computer to interpret. So the next question is, are there languages that are not regular languages? So in particular, is English a regular language? Can we make a finite state automaton for it? Can we make this sort of flowchart system for it to determine if a sentence is grammatical? And so here I stole from, I think it was Steven Pinker. I have one example of what a flowchart for English might look like. So you might have seen these, it's sort of like a common word game. You just follow the flowchart and you get your own sentence. So for example, if you follow flowchart, one thing you can do is, one dog eats ice cream. So that's one possible sentence you can make. Another possible one is the happy girl eats candy, right? And so the question is, can we make this sort of flowchart able to generate every single possible sentence in English? So can we make a flowchart that includes every single grammatical sentence in English you could possibly make? So if I came up with, if I said something grammatical, then it would be on this flowchart somewhere. Is that possible? Okay, so there are some limitations of the finite state automaton. Most chiefly, they have no memory, basically. So I've come up with this sort of like a machine here that uses this finite state automaton model, and I trained it to read Jane Austen's Emma, and after it read Emma, it spit out this sort of text that's based on Emma. And I'll read it here. Your time has been acquainted with Miss Bates with a weakened frame and varying spirits, and consisting of action unusual to her again in Treasury. So you can see sometimes it makes sense, every few words, but it has like maybe the memory of a 5-year-old. So after a few words, it forgets what it already said, and it just starts some other thought, and it doesn't really make a lot of sense. But if you just look at maybe every 4 words individually, like your time has been acquainted, it seems like a person could have written it. But then as you sort of zoom out and you look at the big picture, you see none of these sentences really make sense. Okay, but that's sort of the intuition behind it. How do we construct a proof of this fact? So how can we make sure that English is not a regular language? So maybe we think that English is probably not a regular language because it has this sort of memory built inside its grammar. But how can we prove this? Okay, and basically the idea is we're going to use something called the pumping lemma. And what the pumping lemma does is it gives us a property of every regular language. And we can use this to make a proof by contradiction that a language is not regular. So let me just sketch out the logic here. So if we have a language that's not regular, the proof is going to look something like this. So let me just add a little bit more space. Great. Oh my god. Paint doesn't like me trying to make the image this big. Okay. So the proof is going to look something like this. So suppose I'm going to call the language L. Suppose L were regular. Right? So suppose it were regular. Then it would satisfy the pumping lemma. So L would satisfy the pumping lemma. Alright, and the next step is to show that for some reason this is not possible. So we're going to show that this is not possible. It leads to some sort of logical contradiction. So show not possible. And since it's not possible, that means one of our initial assumptions must have been incorrect. Well, the only assumption we made was that L was regular. We said suppose L was regular, and we showed that that situation is not possible. And so the conclusion is that L is not a regular language. L is not regular. So that's the sort of logic we're going to use with the pumping lemma. So intuitively, let's talk about the pumping lemma. So the intuitive idea is that, let's say we have some sort of finite state automaton, so some sort of flowchart. I'll make a little heading here, pumping lemma. So let's say we had some sort of flowchart. Maybe it looks something like this. I'm just sort of like making a random thing here. Okay, so our flowchart looks something like this. Our start state is over here, our final state is over here on the right, and we have 4 states in total with some transitions between them. And let's say we have the string, maybe let's say s equals a, b, c, b, c, b, d. Okay, so the first thing to do is let's check whether this string is in our language or not. So we start here at the start state like we always do, and then we follow the A, and we land here. We follow the B, and then the C arrow, and then the B arrow, and then the C arrow, and then the B arrow again, and then the D arrow. So you can see that we land up in the final state, and that means S is in our language. So the way we write that is very simply, we use a symbol to indicate that it's in our language. So I'll write a little check mark. Okay, but now the key thing to notice here is that the length of S is what? It's 1, 2, 3, 4, 5, 6, 7 letters long. Oops. So S has a length of 7. But there are only 4 states in our automaton. So therefore, when we ran through S through the flowchart, we must have visited one state at least more than once. And that means there must be in some sort of loop. So you can see right here, our loop is right here. You can go BC, 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 and you can do this an infinite number of times. So, since 7 is greater than 4, there must have been some sort of repeated state, and that means there must be some sort of loop inside of our automaton. Okay, so that's the idea. And so the logic here is that we can repeat this BC as many times as we want. So, we know that A, B, C, B, C, B, D is a valid string, but we could also have like A, B, C, B, C, B, C, B, D, and we know that that would be in our language. We could have A, B, C, B, C, B, C, B, C, B, C, B, D, and that would be in our language. And really, we could repeat B, C as many times as we want. So the way we write this mathematically is A, B, C to the nth power, and then B, D. So n here is just some number, so like BC to the n just means BC repeated n times. So for example, if n were 2, then this would be A, BC, BC, BD. And you can see that we have BC 2 times, because n is equal to 2. But because of our logic here, we can see that no matter what number we make n, as long as it's big enough, it'll be inside our language. So we can repeat BC an arbitrary number of times. And so equivalent, we can say we can pump BC as many times as we want. And so that's why it's called the pumping lemma. It tells us that we can pump some sort of substring within our string and then get another string that's inside our language. Okay. So I've written this here. The loop can be traversed as many times as we want. So if we pump the string that is generated by the loop, we get new strings that are also part of the language. So I've written this out sort of formally here. You don't really have to worry about this too much, but I'll go over with you. So if L is a regular language, there exists some number, some pumping length k, such that any string that's longer than k characters, so remember this only works if the string is long enough, any string with a length longer than k can be divided up into 3 parts. And basically the important part of this is that we can pump the middle part, so this part here, as many times as we want. So I wrote this here. I wrote x, y to the n, z is in L for all non-negative integers n. Right, so we can pump this middle part as much as we want. Okay, so how do we use this to prove that a language is not regular? Well, let's do some example here. We have some language, so I'll write it out here. We have some language, L equals A to the n, B to the n. So in other words, it has the empty string, it has, it has AB, it has AABB, it has AAA, BBB. So it's just, some number of A's and then equal number of B's are the strings that are within this language. And my claim is that this language is not regular. Well, how do we prove this? We use the thing that we just discussed. So the pumping lemma. So assume L is regular. So remember, what's the logic here? First, we suppose that our language is regular, and then we show that it leads to some sort of contradiction, and so that means our assumption must have been wrong, and L is not regular. So let me just show you the logic here again. So suppose L were regular, then L would satisfy the pumping lemma, and then we want to show this leads to some sort of contradiction, so it must not be possible, and then from that we conclude that L is not regular. So how do we do that in this example? So if L is regular, there must be some sort of pumping length k, such that if our string is longer than k, then we can use the pumping lemma. So consider our string A to the k, B to the k. So it's AK times and then BK times. Obviously this is in our language, because it is A a certain number of times and then B the same number of times. And so this meets the conditions of the pumping lemma. Is longer than k characters. It's actually, the length is twice k, because you have AK times and then BK times. And so the idea here is that we need to consider, well, is there a way to pump this string? So actually, the pumping lemma says that the pumping string must be within the first k characters. So that means there must be some sort of substring we can pump, which is just A's. So, it looks something like this. We have KAs, and then KBs. Right, so this is repeated K times, and this is length K. And the pumping lemma tells us that there's some sort of string inside here that we can repeat indefinitely, and we get another string in our language. So for example, we could have A, and then we repeat a bunch more A's. And then we have B, 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 dot, 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 B, B, B. So what do we have here? Now we still have B, K times, because remember we haven't changed that. But now we've pumped some sort of substring within here. So we've pumped some sort of thing inside here, and now we have more than KAs. So we have K and then plus an additional number which we pumped. And the pumping lemma tells us that this has to be inside our language, because remember we can pump the string as many times as we want and we get another string which is inside our language. But you'll notice the number of A's and the number of B's are different. So that means this cannot be in our language, and so we've led to a contradiction. We have shown that this string is in our language, and we also know that this string is not in our language because the number of A's and the number of B's are different. So what do we have to conclude now? So we know this string is not in our language. So obviously both of these statements can't be true. We have reached a contradiction. So therefore we conclude L is not regular. Okay, so that's pretty cool. We've developed this sort of piece of logic, the pumping lemma, and we developed a way to use it to prove that a language is not regular. So now the million-dollar question here is, can we use this on English? So is there some way we can prove that English is also not regular? And I won't go through the whole proof here because it's a little bit tedious, but the idea is that we have some sort of center embedded construction in our language. So what do we mean by center embedded construction? So it means that if we look at our language here, there's some sort of dependency between the A's and the B's. So every A and the number of A's and the number of B's has to be equal. So if we think about it, this A matches up with this B, this A matches up with this B, and this A matches up with this B. And that's what we call a center embedding construction, because you can see we can add stuff in the center here. So we can add more A's and more B's in the center here. And anytime the lines line up like this, we call it a center embedding construction. And it's a fact that we can prove using the pumping lemma that any language that has an arbitrary number of these center embedding constructions is not regular. So there's no way to create a finite state automaton. There's no way to create a flowchart that will tell me whether a string is in this language or not. So this language is not regular. And so the reason that you cannot capture these center embedding construction relations using finite state automaton is because a finite state automaton has a sort of finite memory, so it can't count an infinite number of things. Whereas with these center embedding constructions, we can make it arbitrarily long. So we could have a really big number of A's. So we could have a million A's and a million B's. We can make this arbitrarily large. And that's something that the finite state automaton cannot capture, because it has no way to count up to an arbitrary number. Okay. So the thing is that English also has this center embedding instructions. So how do we see this? Well, let's start with a simple sentence: the dog ran away. We can sort of modify this to make it more complex. So we could say the dog that the fox chased ran away. But now we can modify this again. So we can say the dog that the fox that the man hunted chased ran away. And the point is that we can keep doing this forever, right? And we have the same sort of center embedding construction that we did before. So the dog matches up with ran away, the fox matches up with chased, the man matches up with hunted, etc. And we can make a sentence that's nested together an infinite number of times. And so using this, we can show, using the pumping lemma, that English is not regular. And I won't go through the formal argument. This is a little bit of intuition about how this is true. But that's basically the reasoning behind why English is not regular. And we can do sort of the same proof that we did before with the language A to the N, B to the N. The proof is basically exactly the same with English. Okay. So, if English is not regular, what is it then? What class does English fall under? So the idea is that there are classes of language that are more general than regular languages, but they're less nice, so to speak. So they're more complex computationally. But first, we need some more tools. Hey everyone, so Future Eric here. I've been editing this video, and so I have two things. First thing is I noticed the video is getting really long, so I decided to split it into two parts and leave you a bit of a cliffhanger here. So this is part 1 of the video. Part 2 of the video will be out tomorrow, so I'll hope to see you then. And then the second thing is I noticed that every time I click on the computer, it's really loud. I'm not really sure how to edit that out, so I'm sorry for that. I've decided if I do something like this in the future, I got these sort of like whiteboards, and I can write on these instead, and hopefully it'll be a lot quieter. So, cheers!